Another common problem with exponential functions is radioactive decay. So that's going to be exponential decay, not too surprisingly. So the radioactive element, this is an example, the radioactive element bismuth-210 decays into polonium-210 with a half-life of 5 days. There's supposed to be a dash between half and life. It's okay. We can find the equation for the quantity of bismuth-210 at a particular time as a function of time this way. So we've got A sub t equals A naught, A sub 0 that is. Naught, N-A-U-G-H-T is just another word for 0. So A sub 0, capital A sub 0 times little a raised to the t power. So capital A of 5 equals capital A sub 0 times little a to the 5th power. I just put in 5 days. The units here is days. T is in days. And that's just plugging in 5 because they told us the half-life is 5 days. And what does that mean? That means in 5 days you'll have half of your initial amount. So that equals 1/2 the initial amount. That's what it means that's what the half-life does. Okay, after 5 days you have half as much. You start with A sub 0, you end up with A sub 0 over 2. So 5 days for the quantity A sub 0 to be reduced to A sub 0 over 2. Now notice that if A sub 0 was 0, you would have 0 equals 0. But we don't start with 0 polonium. It just says that after if you start with 0 bismuth, then you'll have 0 bismuth after 5 days. It's not interesting. So we can assume that A sub 0 is not 0. Okay, in fact it says, it doesn't say it's not 0, but we would assume it's not 0 if we're using this formula. Even though it holds for 0, it's not interesting for 0. So you can divide by 0 by A, no you can't. You can divide by A sub 0 on both sides of the equation, right? Cross multiply it if you want. So I guess I wrote that out. Forgot that I wrote that out. So assuming we're starting with some bismuth-210, so that A sub naught is not equal to 0, we get little a to the 5th equals 1/2. And that means A is the 5th root of 0.5, also known as 0.5 to the 0.2 power. That's just to put it in my calculator, or approximately 0.87055. And usually when you have these kinds of things, they'll tell you how many decimal places to round it off to. I rounded that to 5 places, I guess. So what I'm doing is finding the amount of bismuth-210 that remain. Well, I'm just finding the decay rate, A, using the half-life. That's what I did here. Okay. So if I rewrite the equation, I put in the growth rate, 0.87055. So I get A of t equals A sub naught times the quantity 0.87055 raised to the t power, where t is the time in days, because the half-life was given in days. There's most radioactive elements decay over a matter of billions of years. So this one happens to decay very quickly. There are some that decay on a very, very small, short, very, very, what am I saying? Over a very short period of time. And those are radioactive materials that are made in accelerators. They're artificially made. They don't last very long. But this one's a good middle ground. It's in a few days. If we start with 0.5 grams of bismuth-210, how much remains after 21 days? How much bismuth-210? I mean, you're still going to have 0.5 grams of something, but it's just some of it will be polonium-210, right? What's happening is your protons are turning into neutrons. So anyway, the solution is A of 21 equals, and we use this formula here, right? A of 21 equals, the initial amount is 0.5 grams, and then we put this number and we put the 21 days up here. Right? So we get A of 21 equals 0.5 times the quantity 0.87055 to the 21st power. And use a calculator. You get 0.027 grams. And be careful you round it off to the number of places that you're asked to on the homework problems. And that's it, I believe. No, there's more. What am I talking about?